Hello everyone, this is the sixth tutorial for the fitting using a cern root package, and this tutorial will cover quite an advanced topic. That's to use the TMultiDimFit class to do the fit. Okay, this class quite math intense. Honestly, I just know the basic concept, so probably I cannot give you very deep insight on how it works. I mean mathematically, but I can show you uh, some the procedure and the basic concept of it. So with that, we started the very introduction part. So in what kind of situation we may need this class? Okay, suppose we have a function with four variables, and unfortunately we don't know how to model it. That means we don't know which function we try to fit. But instead of uh, trying different mathematical formula, we we think about maybe the linear combination of several terms can do a good work here. So let's say, so we have x. This is x1, x2, x3, x4 as our variable. We can think about their combination, like s1 to the first power, so 0 power, your f2 to the 0 power, such that, and you multiply together and you call this as an f1 term and corresponding to coefficient c1 term, and the first power of x1, the s2 to the 0 power, s3 to the 0 power, s3, f4 0 power again. You define this f2 and corresponding to c2. Okay, so you can understand. Maybe we can think about, since we don't know exact term, probably we can approximate this situation to with a linear combination of several terms together, and each term have the structure of like this structure here. So it's really hard to say that without showing you the formula here. So this is the code I just ran before I go into this tutorial. So I'm talking about this formula here. So you see this is a coefficient, and this is coefficient is that we try to fit, and this is y0, y1, y2, y3, kind of renormalize the x0, s1, s2, s3 here. And this is a certain combination of the power. Y underscore 0 means here. And you can see this time together also have square term, also have three terms together. So in this class, what it did is it determined which term are more sensitive to your change to your data. Okay, so slightly change in this term would cause a lot of change in the fitting result. So first it determined which term you really need to modify that, even you don't know exactly which function is. Okay, so let's define some terminology. Okay, so the CL, the index LTH term would have, x1 to the power of L1, x2 to the power of L2, PL2, such and such here. So we have so many terms. So first we have to reduce the terms or set a limit here. So in this case, we will use a set maximum function to 1000. Okay. The good thing is in this structure is so fixed, so you don't really need to change many parts. I mean, so here, just set the initial here, and what you really do is just to change the the adding row here. Okay, make data adding the row to data. The only thing you probably need to change slightly is here and some condition, and I will explain that a little bit for you. And basically you don't need to change much. Okay, so we have a lot of terms available, so basically we have to set a hard limit. That's in this case is 1000, probably good for all the cases. And also we won't still use all this 1000 term. This is f underscore l terms. Okay, so we need to avoid fitting them too much, because we cannot fit. Okay, let's say you have just 2 points. However, you fit 3 terms. That means you fit too much. That's become the overfit here. So this good example is you have just 2 points, but you use a polynomial to the third power. That's to overfit it. Okay, that's definitely would fit good, but it's just too much for you. Okay, so what you really need to do is to cut it. Okay, so there are a lot of cutting way here. So so instead of using all this term, we need to find a more significant one. That's what corresponding to the fitting end result. So you will set the maximum terms. It will be 30. Okay, so this is L maximum equals to 30 here. Then it would do some internal calculation to determine which are the 30 terms for you. But also it need your some input. For example, what's the maximum power you want? Okay, so in this case, it's set to the maximum power less than 6. So this would mean up to 5 only. So power of 6 x1 to power of 6 is not allowed in any terms here. Only 0 to 5 to power to 0 to 5 are allowed here. And if you set a maximum power to 6 here, I think this is reasonable. And the first condition, you can sort of other kind of find out which term is most significant is to the power. Then the power, there is a term called power control limit. Use the Q symbol here. You can set to 1. 1 is good enough, but what is this for is this, it require the condition. For example, if this is a total power is 1, 2, 3, 4, so the maximum is 6, right? Okay, for this case is 6. Power to the x1 is 6. So 1 over 6 plus 2 over 6 plus 3 over 6, etc. This is bigger than 1. So because we said the Q have to, this Q, the power control limit have to less than Q. So we won't take this guy here. However, if you take the second one, 5, 0, 0, 0 is less than 1, so this is allowed. Okay, so through this process, we can sort of find out the significant terms, but there is still some issue for the last term. Okay, so this is getting nasty, and I'm not quite understanding here. So last term would determined by 2 kind of tests. Well, so the test will be the angle in certain space. So it says maximum angle 10 and minimum angle 10. Okay, so I'm not quite sure this part, so I won't talk too much on it. So, but you can still try to test it. Maybe you change that a little bit, you can fit a lot. Your fit could improve, then you go for it. So okay, so uh, you also have to define which condition is good fit. Okay, so the condition of good fit is to define of set minimum relative error. That means your epsilon here. So if it is less than epsilon value here, the fit will be considered to a good fit here. So epsilon defined as S divided by d squared. The S is the difference between the value, original data value, and the calculated value. And the d squared is just the sum over data square. Okay, so this is a kind of criteria for determine which fit is good. Okay, so let's go to a little bit more detail about it. Sorry. So let's start from the setting part. This is pretty much fixed. Okay. So in this case, I have 4 variable because the 4-dimensional fit, S1, S2, S3, S4, so 4 dimension, and I have 500 data point. So I put a variable here, and I want to use a monomial. That means that it's look like x. How can I say? This x turn x times y times x1 times x2 times x3, something like this. Or you can also use Legendre polynomial. It's also possible. You just change this k monomials to the Legendre. This will be done. Okay. And then you set up the powers. That's the maximum power. Every terms that include in this function to model the data have to be less than power of 6. Okay. Then you set the maximum function. You try the hard limit here, and you set up. Okay, I just want to set 30 of maximum 1000. Then you set the power control limit to 1. That means that your power to the maximum and the ratio, you sum up the ratio will be less than your power control limit here. And you set the sound testing to include the last term here. And then you define by the which one is a good fit. Now it's a 0.01. Now then you all set here. Okay. So the last thing is just to use the fit here from the TMultiDimensional object here and add your data here. So this is X is kind of input from your 4 coordinates x1, s2, up to s4, and D is the value, and E is the arrow. Okay, so then there's nothing very special. You're just using print command, print method. You have several options. C is coefficient. I think I have said print the coefficients is here, and you will see got to 22 turns, and this is the power, and then this is the value here. Also, you can print the formula here. You print the formula nicely here, and if you want to use this function again, you can write it to another file. This time I call the MDF multidimensional fit.c here. I can show you what it look like. MDF.c. So it will look like this. And you can found this function MDF. So you can in your in other file you can include this mdf.c, then you can straight directly use this function. Okay, so finally I just want you to see what happen if I use different basics, what it look like. So I run the code again. Okay, so this is a different basic right now. Okay, so for the polynomial, the basic, okay, so would be x1 is the power of 1, so it's 1. Now power of x, sorry, x0 power of 0, okay, and s1 is power of 1, xx here. Okay, and such and such. Alright, so you might think this pretty complicated. Is that really really useful to real world? I would say yes, because I already see an example. For example, you have a magnetic field and it's not uniform and you don't understand how the particle goes, or you probably cannot measure the trajectory very well or magnetic field very well because it's so ununiformed. So you have unknown function there, and you try to fit some relation to the final product. So final position to the initial position. You probably can use this, and I already see someone use this method before. Okay, so I think that is what I would like to talk about for this part, multidimensional fit, and I hope you enjoy this tutorial. Thank you very much.